Welcome to CircuitValley. This video is going to be about yet another product of mine. In this video, I'm going to show you how I designed and constructed this little USB device which you see in front of you, RFGEN44. It's a USB RF signal generator supported by a very convenient cross-platform application which can run on either Windows, Linux or Mac OS, and very conveniently provided Python scripting or MATLAB scripting environment so that it can be controlled by scientific applications. This little hardware device which you see in front of you is based on this little PCB. It's based on this little hardware. It has a USB and few other components to provide you two RF outputs. As a feature, it provides you third input and output as well, and this is the aux pin, and these aux pins allow you to provide external reference for the PLL. It can also provide you sync output when system goes into sweep mode and generate sweeps of the frequency to test filter or provide a tracking source for a spectrum analyzer. Then this input and output can be configured in various ways: synchronization output, reference input, and synchronization input as well. So it can also synchronize to external devices, sweep frequencies or change frequencies on request on I/O. Hardware is based on a ADF4351 PLL. From analog devices, it can go up to 4.4 GHz. From 35 MHz to 4.4 GHz is very convenient. Provides two outputs. There are two status LEDs, one for power, one for PLL lock. This is my second revision of this project, and last time I published a really crude version of it, and application was also not that advanced. Now I have updated the Qt application and also provided a Python application so that you can easily use this device anywhere you go. And now this device also supports standalone operation, so there is a possibility to save configuration on the device. So when you just apply power to it, and this device will start working. So these are the status LED, the power status LED, and in front you got PLL lock LED. When the blue is lit up, you have output or rather PLL lock on the output signals connectors. You can of course connect various kind of adapters to it. For example, this SMA to SMA adapter to convert into various forms. There is enough place between the connector and the plastic housing, so you can connect any kind of adapter or do whatever the things you want to do. Both of the outputs are 50 ohms output, so very well suited for any kind of application. We'll try to connect this now to the PC application and test it on my spectrum analyzer, which goes up to only 3.2 GHz, but we have oscilloscopes which goes to 50 GHz or even 8 GHz. So we'll be able to completely see the whole signal, how good or bad it is outputting, and what's the signal level as well. On the lower level of frequency, output is rather high in amplitude, but as you go up in the gigahertz range, output drops a little bit. That we will see. You can definitely connect such things as well because it's generating signal, so you get a PLC output very easily. It's very convenient. SMA keeps the cost and the total device size small, and that's why it's pretty nice to have. Now I'll show you the PC application so that you can get familiarized with what is it we are dealing with. I'll show you the application running under Windows, and then I'll show you under Linux. So this is a USB device connected. Windows got detected. Everything looks good. We also see the application on your screen. You can see this is the RFGEN repository from GitHub, and I have downloaded the whole repository, and this is the Windows GUI, and in this Windows GUI you have the DLLs from Qt. These are standard DLLs, and this is our application. When you launch this application, you see this device shows you serial number on the bottom and on the title as well, which particular device have been connected to the computer. There may be multiple devices connected. Currently we see only one device connected, serial number 5. Let's connect multiple devices, and then we will see how does it look. So now you have serial number 5 and serial number 9, both are connected, and we can clearly see both are listed. You just have to select whichever device you want. By default, if you have only one device connected, it automatically finds that device and opens that for you. Here on the interface, on the top you have version information and the firmware version information from the device as well. I have connected my device number 9 actually to my oscilloscope, which is for primary testing is just Rohde & Schwarz, and we will try to test this application with this guy. Maybe I zoom it out a little bit. So now we see it better. Okay, so when I turn on the device, you should be able to see the 100 megahertz signal which has been configured. Maybe I'll start with the lowest frequency. So because this oscilloscope is only 300 megahertz, we will be able to do only basic testing. So 35 megahertz configured. Let's write to the device. So as a tour to the GUI, I'll tell you that here you set the frequency, whichever the frequency you want to output, and these are sweep and hop. If you program a frequency, start frequency, for example 35, and you want to sweep till 40 megahertz, then you can write like that. And step, you can configure step in the 10 kilohertz step. Of course it has to be between the range. You can start the sweep once, so it will loop through the required frequency and automatically goes through the frequency and show you whichever the frequency it is currently working on. You can loop as well, so it will now loops all to the frequency and start one more time with 35 once it reach the required 40 megahertz. Very generic operation. If you have if you want to do hop, then you can select 35 to 40 and select a 5 megahertz here. It will automatically give you hop. You cannot of course set more than that. If you want, we can set 100, maybe 100 megahertz and start. So it will automatically do hop between 35 and 40 megahertz. Right now output is off. You can see the output off. If I connect the output on, you will see the 35 and 40 megahertz being outputted onto the oscilloscope. So it's as easy as that. Let's turn off the output for now and stop the operation. And this is the aux pin function. It sets the sync out and sync in. So for the sake of display, I'll show you. When you select the sync out, so you will get a trigger when the sweep starts. So every time it goes through these two frequencies in this hop case, it will give you a trigger when both of these outputted, not in every single frequency change, but when the whole sweep operation starts. And you can also have an external reference. External reference frequency is in the advanced. By default, I expect 25 megahertz. You can set this frequency 25 megahertz to, you can set this frequency from 10 megahertz to 250 megahertz as for the specification from the device. I would rather keep it to 25 or maybe to 10 megahertz if you're getting it from GPSDO or something like that. Device now also supports the standalone operation. You can program these parameters. For example, you can program the output frequency and sweep as well. This new version of this hardware, this new device which I designed, supports in-device sweep. So you don't necessarily need PC for any operation. You can configure the device using this GUI once and then program it to flash. And next time when you use the device without a computer, it will automatically remember whatever you have written and it will automatically output that thing, including this aux pin functionality, sweep and frequencies and everything it will be remember. So if you want to do in-device sweep, means it will do standalone sweep and you can program the flash. So it will automatically go to 35 and 40 megahertz and automatically output the frequency. So this is for standalone operation. These two buttons, you can erase the flash as well, and this memory will be completely erased and you will have nothing on the memory, so that you can easily reconfigure the device. And when you do program flash, it automatically stores these information into the flash memory of the device itself, and you can do standalone operations. In the advanced control, as I showed you, every single configuration which is possible with the PLL chip from Analog Devices ADF4351, you can refer to the datasheet, and the documentation from the Analog Devices is available here as well. And every single thing which can be set, maybe for some reasons, this counter divider values and everything else, and reference divide by 2 and everything is automatically calculated. You can freely set whatever you want and happily enjoy evaluating or controlling this device. So for now, for this operation, I'll show you a few things. For example, I'll show you the frequency, and let's start evaluation. We will set the frequency to 35 megahertz first, and I'll show you the signal quality and everything else. Right now, this oscilloscope is not 50 ohm terminated, so real signal will be only visible on the spectrum analyzer. This is right now I'm showing you for the sake of evaluation of this software, that how well it works and how reliable it is. Let's turn it on. So I have not written it. That is also one use case. When you change the parameter, you have to write it, or you can also select the auto write and it will automatically write the settings to the value. This option is done so that you can freely change multiple settings before it being applied to the device. If you select the auto write, every time you change something, for example, you see the registers value on the bottom, these are raw registers. Every time you change something, it automatically write to the device. But if you do not click auto write, you have to manually write it and then select RF on. So if I change it to maybe 50, I'll show you, and I write it, then it will automatically change it to 50. And if I do auto write and I slowly change it, then it automatically of course updates to the device. So we'll go back to 35 megahertz. Maybe disable auto write for some now, and we'll go zoom in. We'll see how does it look, the real signal. So yeah, 35 megahertz signal, and it is not 50 ohm terminated. You see this little artifacts or this reflection in the waveform is not properly terminated, but it's good enough for the test of application and the control itself. So one thing I would like to mention, that when this application supports multiple device operation, first thing it supports that it shows you the exact firmware information from the device, and it also, when you have multiple devices connected, you will be able to click this identify button and you will see the LED blinking on the device. And as I'm showing you currently in the video, you see this LED blinking. When I click the identify, LED of this device blinks, and it here shows you device busy as well. So this is a nice feature when you have multiple devices connected to a same computer, and when you want to change quickly the device, you can of course change quickly device. Changing device does not do any changes in the device state, so you can have multiple applications running at the same time, or even one application controlling same device. So it does not toggle the RF output state or something like that. Maybe I'll show you how the two devices get controlled at the same time, connected by the same application. I have serial number 5 and serial number 9. You see in this, from this device, serial number 5 disappeared because I'm currently working with this device on serial number 9, and here on serial number 5. When I close it, you will see both of the device appear one more time. So 5 and 9 both appeared. So this is very reliable and very well tested method, and whichever the device open, it shows you on the top serial number of the device, so you can easily identify which device you are dealing with. Identification of the device is primarily depend on the serial number itself and VID PID. VID PID is same for every device, while serial number is of course different for every single hardware. So let's get back and we'll try to output different frequencies. Maybe we'll output like 35.1 megahertz, and we'll see if it changes. So if you output 35.1 megahertz and write it, of course it changes. So you can set the resolution in 10 kilohertz. This ADF4351 allows 6 kilohertz, around 6 kilohertz step. So I have rounded that value to the 10 kilohertz range, and that's good enough. So when you write 100, you get 100 megahertz, nice clean signal, and signal amplitude is around, how much is it? I'll say 500 millivolt per division. So 1 volt peak to peak plus 1.5 volt, maybe 1.5 volt peak to peak. Now we'll try to do sweep from 35 to maybe 60 megahertz, and we will do sweep frequency change of maybe 2 megahertz in a step, and we will do it at a 50 milliseconds rate, and we'll loop it, and let's see if it works. So RF on. When you do sweep or hop, it automatically selects this write, so you don't have to manually write every time. And now let's see, does it work? Yeah, it works pretty reliably. So you see this frequency changes as we slow down or we go through the loop process. You can stop if you do not like it. It is very fast right now. 100 millisecond start sweep. Works pretty reliably, works pretty well. So sweep also works if you want to see the hop. So we'll show 35, 40, step is going to be 5 megahertz. So when you configure it like that, you get a hop. So start sweep. So you get only 2 frequencies, and signal is switching between 2 frequencies. This thing you can of course program into the device firmware itself. And when you do program flash, and you have to select of course for sweep in device sweep, and you program the flash, it automatically configures it. If you want, I can show you. Right now the sweep is configured, and I'll do stop from here, and I'll disconnect the device, and I'll from the USB, and I'll show you that it automatically reloads the sweep parameters, and it will start sweeping automatically. You don't have to necessarily need a computer or do anything else. So I'll disconnect the device number 9, and now I'll power it without connecting it to PC. Now device is powered from a power bank, and you see it is automatically doing the sweep without our operation or control of the application itself. So standalone operation is also quite reliable and works pretty well. This device is support USB HID, Live HID from Python and everywhere else can be easily used and very well supported. So you don't have to necessarily configure the device to be, sorry, we maybe did the wrong device. Now program flash. So we got 40.1 and 40.1 megahertz. This works really well. If you set 42, and we get 42 megahertz. So it's very easy, very well intuitive software. And maybe I'll show you the Python application which I have available for this same operation. Whatever you can control with this application, you can control with the Python as well. Maybe not every single parameter is available directly to controllable, but of course you can go in the source code and modify yourself. But all these parameters, writing flash, reading flash, writing sweep, and everything else can be of course configured through the Python as well. And it's a small script provided by me automatically as a binary and as a source as well. So you can happily program your RFGEN44 RF signal generated devices. So let's go to the Linux and we will see what we can do there with the. So now we will perform the test on Linux environment. I'll be using Ubuntu as my target machine, and we will see how easy it is to operate the same device in the cross-platform environment. First, I'll show you the same Qt application, and then I'll show you the Python thing or Python script which I have written for it. Python script is of course fully capable to do any operation which you may require to change frequency, start program sweep, program flash, erase flash, and whatever the thing you want to configure or prefer to change in the device operation. Of course, device can, as mentioned, work in a standalone operation, so may not necessarily need a computer. Device number 9 connected to oscilloscope for the sake of verification of the software. Now we got the same application running under Linux, and you see it changes a little bit, and in Ubuntu it looks a little bit different, but the primary information stays the same. You get the firmware version or device version, same stuff. You can choose the different devices, RFGEN 5 or 9. And in Ubuntu it looks a little bit different. The same device get listed twice, the one which is open and the whole list as well. But you can still do the same. Maybe I'll change and write to the number 9, and let's write it. And frequency changes to of course 100, what we have already programmed. And same stuff, to write 35, it does the same thing. 100 to 500 loop, maybe I'll change it to 35 to 50. And every 100 milliseconds loop, start sweep. I think the step is too big, maybe I'll stop it. You see, same operation under Linux, works exactly the same, there is no difference. And you can of course go in the advanced control and change whatever you want. Here you see, as the sweep frequency changes in the loop, the frequency or registers changes as well, of course. So I'll stop now, and I'll show you the same application in environment of Python. So this is the Python script I have written, and this script, when it runs, it looks something like this. Maybe I'll make it a little bit bigger. It's written with the Python libhid, and it allows you to of course set the frequency, list all the devices, select the serial number, write to the device, get firmware information from the device, write to the flash, identify the device, erase the device, and control the RF state, program sweep, select the aux functionality, start frequency, stop frequency, and step frequency for the sweep, and of course step time for the sweep as well. It does not here directly allows you to configure, for example, you can say that it does not directly allow you to configure what's the R counter value or something like that, but it is available as a source, and you can of course modify the source. Maybe I'll show you, and we'll go through the source a little bit. So these are the registers values, and here in the class everything is specified, R counter value and default, everything. So you just modify here, and rerun the Python script, and it will give you whatever the value you want. Not necessarily need to write application or compile yourself. I will provide the binary as well for the Python script, and these binaries can of course be directly used without. This is the binary, does exactly the same thing, and does not necessarily need support of the computer or the programming knowledge or anything else. And now we will see how many devices are listed. You remember we have 2 devices, and we will see if it really display both of the devices. So we have 2 devices. One is our CircuitValley RF generator number 9 and number 5. Both of the serial numbers are listed. So when you have multiple devices connected, for most of the operations, you will need to specify which exactly device you want to communicate through the serial number specification. If you have just one device, you don't need to specify the serial number. It will automatically find that device and use it. I'll show you. Maybe I'll write the frequency to 35 megahertz. This is the megahertz value. You can specify the same 10 kilohertz interval, and I will do a write operation onto the device. Okay, so it says multiple devices have been found, required serial number to be specified. So we will specify the serial number with -s or minus serial number, serial. So -s, and we'll copy the serial number for number 9, and let's see. Failed to open the device. It failed to open the device because device is currently open in the GUI application. So we close it, and now we'll try one more time. Yeah, so you see the frequency changed to 35 megahertz, and of course it wrote 58 bytes to attach a device. This is more of a debug information that it exactly wrote to the HID device and everything else. So if you change it to any other value, it will of course update to that value. So it is unable to get the trigger or something like that, so that is not measuring properly, but oscilloscope is not measuring properly, but of course it works as you expect it to be. And now I'll disconnect the number 5 device so that you can see that you don't necessarily need to know much or have information about the serial. Now I'll do a list. So in the list we see that device specification or the device list shows the VID PID list. There's only one device found, and when you try to do write, it will not warn you for anything else. So validation have been applied to frequency as well. Of course you cannot set it to 30 megahertz. It will warn you that frequency is invalid, and it is not allowed to set such a low value. So it's as easy as that. If you want to write, for example, I'll tell you, if you want to write the device operation, or you want to do standalone mode programming or flash programming to the device, or the flash programming to the device, we'll just do help, and for the flash programming you do flash write the T command, and you specify the frequency, of course, which you want to program, and maybe 45, and you do like this, and it of course program the flash. I'll disconnect the device now, and I'll show you that it automatically loads the required 45 megahertz value. Currently it has not loaded because we have directed only to write to the flash and not to the current parameters. So I'll disconnect the USB device. You will see the signal disappeared, and now I have connected again, and it of course loaded into the 45 megahertz value, and you don't necessarily need to use the computer to run the device. It supports the standalone operation. You can use power bank to generate the signal, and it works reliably well. So what else can we test? We can test the sweep as well, because this Python script is not supposed to be running in the background, so it only supports the in-device sweep. Let's see how do we program in-device sweep. So we program sweep by writing P, and you have to specify the start frequency with P. Start frequency 35.0, and stop frequency for 50, and you don't need to say 0, but 50. Step is 100 milliseconds. The step value is in milliseconds. Sorry, we have to first specify the step frequency. Step frequency is 1 megahertz, and J step time integer in milliseconds. So milliseconds, 100 milliseconds, and it automatically programs this parameter to the device. and we'll see if it works. Okay, so it wrote and it started the sweep as well, because the device is not correctly connected or opened by the program, and right now it's doing in device sweep. It's programming or changing the values from the flash itself. All the operation is done in the firmware itself. So it is as easy as that, and works reliably well. And if you want to do, for example, erase the device and not have this configured, you can just say erase, and of course device defaults to wherever it was last time. And of course you can control the RF output as well, and we'll say 0. Output will of course disappear. So we have tested list F serial number, to specify serial number, device identifier. You can say of course device identifier, and it will blink the LED and show you that this is the device you were dealing with. It shows you the which device it founds, of course. If there are multiple devices, for example, I'll now connect the device number 5. So it says the serial number to be specified. That minus serial need to be number 9 or something like that. So it, of course, running the device identification routine on the number 9, it will blinking LED for 2 times, and then you will be able to easily identify which device it was. What else we can test on RFGEN is we have aux select. You can specify 0 for the sync output, 1 for sync in, 2 for external reference, and do whatever you want to do with it. So now what I will do, I will connect this device to a spectrum analyzer so that we can exactly verify its output performance, and we will see if how good it works. We will also try to connect it to a fast oscilloscope so that we can see signals in the 4 GHz range, because my spectrum analyzer only goes to 3.2 GHz. So I got my spectrum analyzer from Siglent. This goes up to 3.2 GHz, and you can see the start frequency is 0 and stop frequency 3.2 GHz. We'll connect our this little RF generator device to this guy. So you see I already connected to the PC, powered on. We will connect through the SMA cable to this guy, and we will see how does it work. So I have connected the device to adapter like this to BNC, and we will now connect this guy together with the BNC cable. Let's make it tight, and device is connected like this, and on the other side we will just have spectrum analyzer connected. BNC goes in there. So we got our device connected, hooked up to a BNC, SMA to BNC adapter, and through SME through BNC cable to our spectrum analyzer. Now we'll operate it from the computer. So we have limited the span from 30 MHz to 500 MHz. So let's output a 50 MHz signal. We'll write, maybe we'll select auto write. Let's turn on the output. You see that at 50 MHz I got -1 dBm of signal available. Primary output is at 50 MHz. The spectrum analyzer also verifies that, and the harmonics available on as it is a decent what you call it, it's not completely pure sine, somewhat of a square wave at this low frequency. So you see harmonics are available. As we saw on the oscilloscope, it was not completely a square wave, so of course we can see some harmonics. Let's go to maybe 100, similar amplitude of around -1 dBm. So let's go to 150 MHz. A little bit down amplitude, but it's good enough for our little signal generator. 300 MHz, and we see around similar amplitude. As you remember, oscilloscope had shown a significant drop in the amplitude when we saw 300 MHz because it was a bandwidth limited device, and now we see at 300 MHz -1.44 dBm. Let's go to 400 MHz. It automatically went to 400 MHz, and signal amplitude dropped a little bit as well. So now we will try to show you that how well the sweep works. 35 or maybe like 100. Or maybe like say 300 to 500, and we got step of 10 MHz, 100 millisecond loop start sweep. So you see it's sweeping, and now I'll change the spectrum analyzer span so that we can see the signal from 300 to 500 megahertz. Now I'll change the signal span or spectrum analyzer view to 500 megahertz to 1.6 gigahertz, and we'll see how does it work there. And now change the span to 500 megahertz to 3.2 gigahertz and selected the frequency of 1 gigahertz, and you see at 1 gigahertz is showing you the output around 2.3 dBm, minus 2.3 dBm into 50 ohms load. And let's set it to 2 gigahertz. At 2 gigahertz we see output is very decent, clean, because the harmonics are not visible there. At this level of frequency, higher frequencies, output is better than in terms of harmonics rather than on lower frequencies. Amplitude is dropped. Amplitude is a little bit dropped, and at this amplitude is dropped to around minus 5 dBm, but at this level it is quite expected. If you want, like, you could go to the 4.4 gigahertz. Of course, it's not visible, so let's go to 3.1 gigahertz. And at 3.1 gigahertz as well, amplitude has output has dropped, and we will go to 2.5 gigahertz. At 2.5 gigahertz, amplitude output has dropped a little bit, but the same 2.5 gigahertz signal is available. So of course this device is working. So as said, device operation is quite easy and works really well. Maybe I'll now program the flash with this 2.5 gigahertz frequency, and we will see if it is device also works in the standalone operation. So right now the device is connected to a power bank, something like this, and it's not connected to a computer, and you see the frequency which we programmed, 2.5 gigahertz, is available at the output, of course, and you see the output PLL locked, LED as well. This get locked only when the PLL is locked, and output is available on the device output. So this standalone operation allow you to do anything whatever you want to do without the need of a computer. So we'll go to now my big oscilloscope, and we will try to see how well it works or how decent it works in high frequency ranges. To be able to use the device with my electronics, we will try to use this SMA adapter, and we will connect it to my 20 gigahertz module, and we will see how easy we can operate it. These modules, these are high sampling oscilloscope. They are very sensitive, so we will not be able to output much signal amplitude into them. Be aware that don't feed very high voltages into them. So let's connect them and we'll see. First challenge which you face this oscilloscope is that will require a trigger. You will not be able to trigger from the waveform. So I'll maybe install an adapter, something like this, and we will be able to get the waveform from the positive channel, and we'll try to feed it into the trigger, and so that we can see the signal. So now I'll select the trigger to external clock, external prescaler. So we got our signal at 2.5 gigahertz, and if you want, maybe we can measure it as well. Pulse, amplitude, timing, measure period, measure frequency. It's around 2.5 gigahertz. Now I'll change the frequency to 4 gigahertz, and we'll see how good is visible on the oscilloscope. Let's change it to 4 gigahertz flash first, and then it is already written, and we see this at higher frequency signal amplitude or signal quality is a little bit better. So we have around 4 gigahertz signal. It's actually exactly 4 gigahertz. The measurement is not very, it's not exact measurement. It's only measuring on one period or something like that. So we see a good, decent 4 gigahertz signal, and around amplitude of, how much amplitude it is? Amplitude of around 240 millivolts into a 50 ohms load. Now I set it to maximum 4.4 gigahertz, and do you see a 4.4 gigahertz signal? Yes, we see exactly a 4.4 gigahertz signal. Measurement amplitude around 200 millivolts per division. Around 200 millivolts signal amplitude. Works reliably well at 4.4 gigahertz. Oscilloscope has verified it. Works pretty well. So that's it for this video. This device is available for purchase, and if you want and interested in this device, you can buy this device from CircuitValley shop. And this is completely supported product and will be available to the customer so that they can evaluate or use this a decent small low cost RF signal generator for their projects. Can be used for various things, and works very reliably. Visit my website www.circuitvalley.com.